So for the final part of the lecture, we have the empirical evaluation. So the authors considered a few data sets. We have these 7 data sets that are divided into synthetic and real. And the synthetic data sets are, they also refer to them as the toy data sets, mainly because of their sizes. So the number of class and relation types is quite low, as you can see here in the first 4 rows. And for the real data sets, we'll see what they are in just a moment. We have greater numbers here. So we have relation, they even have more, but they capped it at these, at least for DBpedia, at these numbers, just to keep it manageable. And then, they kept these numbers quite uniform for sample KBs. They kept it at 5,000, trying to see if that was enough to get good numbers. And a little bit more information on the positive versus negative classes specified and inferable classes and relations inferable for each class. So you can see that it's quite imbalanced. So you have the negative parts are much more dominating in general. So just to get a glimpse of what the data looks like, what the domains look like, at least we have, this is one of the toy data sets. The family tree data set, the ontology says encodes all the family relations, right? So mother is a parent that is female, sibling, you have, the same parent and two different individuals, grandfather, we all know more or less what this is. So we have facts which state the gender, in this case considered as either male or female, and who's parent of who. And then some examples of inferences that you can do, like in this case, if you take Della and Huey, Della is a parent of Huey, and Quackmore is the parent of Della. So then Quackmore is the grandparent of Huey, right? The same kind of thing for sibling and great aunt. And in the graph here, we can see that it can get pretty complicated. There's 28 kinds of family relations. Not a lot of of these we generally don't refer to in our everyday lives, but they do exist. The other one is a countries data set, which is also quite similar, but it's just a different domain, where we have the ontology says, which country is located in which region, who's a neighbor of whom, subregions. So region R has a subregion S, and who's, like I said, who's a neighbor of whom. And some inference examples, for instance, Western Europe is a region of Europe, and Belgium is located in Western Europe. And because we have it here, then we can infer that Belgium is in Europe, which we didn't have in the facts. So quite simple. So DBpedia, for the real data sets, DBpedia encodes, it's a well-known data set, encodes knowledge from Wikipedia. It's massive, has thousands of classes and relations. And as I mentioned just a moment ago, the authors restricted to the 101 most frequent classes and the 518 relations that allow for the greatest number of inferences. There's not much discussion about this in the main body of the paper. There are more details in the appendices, however. The Claros data set is a catalog of archaeological artifacts, in this case much more toned down, with 33 classes and 77 relations, but still bigger than the toy ones. And in both of these cases, the authors sampled using a subset of the original knowledge graphs using 200 individuals. So just to see how well they could do with this kind of sampling. And finally, the Unified Medical Language System, UMLS, it has the domain is biomedical domain. It has 127 classes and 53 relations. And this is interesting because it has more classes than relations. The other, the rest of the data sets was the opposite. And this is one of the examples that I was mentioning where they only have rules. They don't have facts. It's just the set of rules, and the authors still can generate a data set of 5,000 sample KBs based on these rules. The results are very, very good. So as we can see here, accuracy, they do accuracy and F1 also for divided in the specified classes, the inferable classes, and the same for relations specified and inferable. And we can see that all of these numbers are quite close to 1. So it's a massive success for these tests at least. And the lowest numbers I think are here. So for countries, so for the S2 and S3 data sets, in the countries relation data set, you have the inferable relations are the ones that do the most poorly, but they're still very, very good at over 91%. The further experiments that I found the most interesting were the ones that I mentioned at the beginning, where they corrupted the test data. So in 2 ways. So first, taking away randomly, removing one fact that could not be inferred. And the other kind of corruption was the inconsistency, where they randomly chose one fact in each of the test samples and added the negated version of the same as another fact. So something that should not happen. And how they did was also not bad in a way, in one way of seeing it, but much worse than the numbers we just saw. So for the reconstruction of the missing information in DBpedia, they could do it 33.8% of the time, and Claire's 38.4%. Inconsistency was much better, though, 88 and 96 approximately for these 2 data sets. This is, again, the spirit behind these tests is that if you do this on a classical KR approach to these problems, you'll just not get an answer. So that's what the authors underscore, where at least here you're still getting an answer. And in the case of inconsistency, you're getting a good answer. So you can see it as a kind of graceful degradation, where they're only randomly removing like one fact and choosing one fact and doing the negated version. So if I were the one doing the experiments, I would have liked to see how that keeps on degrading. But they had done a whole bunch of other experiments, so I guess this is for future work.
I had a question.
Yeah.
So I'm trying to understand the novelty of this approach. In the paper, they don't really compare this to anything but the neural theorem prover. And
yeah, it's coming up.
Yeah, and the results are relatively similar. So just for understanding, like if this would be done classically, right? So if we don't really care about necessarily the performance, so what would be like a set of algorithms that you would say use for these type of problems, and how would that performance compare to this, since they don't really mention it in the paper?
How would the classical approaches compare, for instance, for missing information, for inconsistency?
Yeah, for this type of problem, for other ones, yeah.
Well, that would be kind of opening a whole can of worms, because there's, like I said, a whole area of KR for each of these, essentially. So it's not like you can just pick one and say, this is the state of the art, let's compare. And again, if you're only removing one fact, I think the classical approaches would still do quite well, but it's hard to say, really. It's hard. You would have to really work hard at designing a fair experiment. So I think it's the novelty that the authors are driving at is, look, I mapped this to learning a kind of neural model that is, cleverly crafted. It works really well, at least for this language and for these data sets. And I can still throw at it the kinds of things that will typically really, really complicate things for classical approaches, where you have to develop these very involved tools to be able to get around and still be able to provide an answer. And it still does pretty well. I think that's, if I would have to make the case for the paper, that's what I would say. Maybe Paulo, you can add if you want to add anything.
We got a follow-up question.
Yeah, slightly different question. I was curious about the scaling of this approach. So basically, like, they have this hyperparameter D, and at the end of the day, right, they're using a recurrent network that is going to be unrolled across like the number of elements in your database. And when they sample for like up to 240, and it seems unlikely that they would be able to scale to like bigger than 240 because of vanishing gradients and other problems. So I'm curious, like, did they discuss this in the paper, and also like how would they address like scaling in general to like say a database with 1,000 predicates or something?
That's a great question. I also have the same kind of uneasiness when I was reading it. Like, how would it scale? They don't refer to it in the paper unless I missed it. So it would be interesting to see if it does scale better. I think it's one of its weaknesses, though.
Actually, another question, which is in a knowledge base, right? They use these like triplets. I'm curious about like, that seems like a common way to represent information in a knowledge base, but is that a limitation in any way, or is there like work that tries to get around that?
The limitation that one could say that exists in that sense is that you can only represent unary or binary relations, right? So that's one of the assumptions that the authors make, and it's one of the assumptions also that RDF makes. In RDF, there's a way around it, and they developed this concept of the blank node, where they say, okay, if it's ternary, it's a relation between the first guy and this blank node, which is another thing. And so you can like keep chaining it, and like saying, for instance, if I will give a gift to Paulo, what is that? It's a ternary relation, right? So it's Jerry, it's the gift, and Paulo. It would be Jerry giving the gift to Paulo, and that the gift to Paulo is another triplet, right? But that would be even worse in the sense of the scalability question that we just had, where it's injecting even more relations into the thing, right? So it is a limitation.
Got one more question.
It's a follow-up to the one of the first previous question was regarding with the scalability of an LSTM. I'm wondering, because due to the vanishing gradients, if you scale it up to more rules, could you possibly replace the architecture with like a transformer that is like a long, there's these different variations like long former, in order to get scalability to these very long sentences, or at this case, these long database of predicates, for that.
That sounds completely reasonable to me. It's way beyond, I think, the scope of the paper, though, and it does sound like a reasonable approach. One thing that I would like to point out is that even though you can encode long derivations of rules, typically you don't see them in the wild, right? So you don't see like these very long chains being encoded. So I think it's reasonable to consider that there's an upper bound on the length of the derivations that you can have. Of course, in detriment to the generality of the approach, but it won't come up in practice as much as one would think, and depending on the domain, of course. But. All right, so just to finish up, the authors, they provide a visualization of the embeddings and how they, this TSNE embedding of how the individuals look like in the country's data set, essentially just to validate that the way that the model learns these embeddings makes sense visually, right? So you can see how they group together in ways that they make sense. Just take a look at the paper for this. The comparison with the neural theorem prover is one of the questions that we had. Also, the RNs come up on top, not by that much in some cases, but typically they do win. But the neural theorem prover is the kind of rules that they encode are restricted to positive foreign clauses, so kind of like a prologue. And the authors point out that it's trained on the same knowledge graph as the one that it is evaluated on, which is not ideal. And also it has performance issues, so we're only able to compare it, as we can see here, on the synthetic or the toy data sets. Last couple of experiments where they do the update, the number of updates, updated iterations to see if they can get away with doing less, and also the number of layers per relation that they have. I mentioned this briefly, and you can see that for different kinds of relations which require, they call it hops, the inference steps that you have to do. So for father, it's just 1. For sister, it's 2, because you have to go up to the parent and then go down and then check that it's female for the sister. Great grandson, up to 5 hops, and this maps quite directly to the number of update iterations that they have. So it's kind of like a validation of that. And also for the inferable relations with 1 prediction layer per relation, and 1 for all. So 1 for all is not enough, because you can see that it drops significantly in some cases the performance. So you have to actually have 1 per relation. All right, so finally, this is essentially Kautz level 4, where symbolic knowledge is compiled into a neural model quite directly. It has strengths. I think we discussed this during the questions. So it's elegant and it's effective. Very promising experimental results. I think there are a lot of more experiments that could be done to see how they do. Some limitations, not yet capable of producing explanations for the inferences, and data log is quite weak as an ontology language. If you compare it with like OWL, or semantic web languages, also like data log plus minus existential rules, it is where they actually come up with, for instance, value invention, like saying every person has a father, and then you can do it, these kinds of inferences. These are not considered. So for future work, I think that they could incorporate other forms of reasoning. Also, this is mentioned in the paper, such as non-monotonic and things like argumentation-based reasoning. These are not at all considered. That's it.